And that random stuff is kind of relevant, because as you guys are going around, the algorithm one hit me, because when we look at least from the teacher perspective, when it comes to exams, you can pull up test banks for questions. And in those test banks, they ask, well, we've got questions that are algorithmic, right? Meaning it's the same question, but the test bank automatically changes the numbers so students can't cheat by copying off of each other. Right? Or at least that's the theory behind it. So what is the algorithm for this? So if I asked you to convert 2.283 feet into inches, what would you do? Okay. I just heard multiply by 12. What you just came up with was the algorithm. When we go through and talk about conversions, we don't want to do algorithms. Because I'm going to make the argument that if we try and do that, you're wrong. 2.283 feet times 12 equals what? I should have picked a number I could multiply with. 24 point something. Actually, it's probably going to be 25-ish now. Someone have a calculator handy? 27.396 feet. And you're going to be like, well, but no, I converted to inches. Does anything in your statement for this work show anything about inches? No. Does anything show anything about getting rid of feet? No. So if we follow just the work, that is what your answer is. You've internalized some information behind this. You've internalized the process, or as Greg and I were discussing, perhaps the heuristic, and instead have now only done the conversion as an algorithm. You just multiply by 12. That only works if you've done this process or this calculation lots of times, right? Which you probably have. What I want you to think about when you do conversions is not just, well, I multiply by 12, but what else is associated with it that allows you to make this transition correctly to 27.396 inches. What is missing from your calculation? There are 12 inches in 1 foot. Okay. The feet now cancel, and you're now left with inches. Now when you run the calculation, it comes through and it equals exactly as it is. Okay. This shows the complete work. Okay. It shows all that kind of implied knowledge that you embedded into the algorithm. Okay. This is one of the debates we'll encounter when we move into the second unit, is because you're like, well, it's obvious, you just do that. It's obvious because you've already done it hundreds of times. What if we move to a system that you haven't done hundreds of times? Now you're up an unpleasant creek and you don't have a paddle because you have no process by which to decide how to place the 12. Should I multiply? Should I divide? Okay. So you need the heuristic, the larger information behind it, to allow for that conversion to come through. Okay? So just think about that when we get to conversions. Because algorithms popped up, I wanted to at least address it because it broke something in my brain. Okay? Which gets us over to this. I forgot why I jumped back to Thomson. Oh, I think I know why I jumped back to Thomson. The end of Thomson's model, he said we had electrons because he could find those electrons. He then said the electrons had to be the plums in the pudding of positive charge. Right? Okay. As we add to that, Millikan and Fletcher came through and then studied electrons a little bit further, and they were actually able to determine the exact charge. And the only reason we talked about that experiment is because of the brutal tedium of trying to visualize an oil droplet hovering in a microscope. I just think that's kind of cool that they did that, right? So questions about either of those two? Solid? Okay. This is where Rutherford comes in. Okay. Rutherford went through and said, okay, let's test Thomson's model. Okay, let's try and come up with a way to observe if his model is correct. Because in Thomson's model, really the only thing that exists are electrons, and then there's just this kind of empty, foamy space of positiveness. Okay. So what he was able to do, thanks to some other people's research we'll talk about in a second, was he was able to take a beam of alpha particles, and alpha particles, because I don't want to write it all out, I'm just going to write, come on, I'm just going to say alpha. Alpha particles are positively charged things with a significant mass. Okay. So if I fire a positively charged particle at Thomson's plum pudding model, if it sees these electrons that are now these larger objects, at best they're attracted to the positive or to the negatives because they're opposite charges, much like the north and south end of a magnet. Okay? They're moving fast enough, they're with enough mass, maybe they would hit and ricochet a little bit, okay, or shift a little bit, but because they're attracted towards it, for the most part, they're just going to pass straight through. There's nothing for them to repel away from, okay, because the positive charge doesn't have enough mass inside those, inside our atom. Okay, so what he does is he sets up his alpha beam and aims it at a piece of thin gold foil. Okay, why thin gold foil? Because if we hammer it thin enough, light can pass through it. So we figure we have a small enough particle like an alpha particle, it will pass through. And we can prove that it does pass through. And what he sets up is a detector on the other end of it. Okay, if Thomson's model is valid, what would we expect to see? Okay, so the detector just lights up whenever an alpha particle hits it. Thomson's model is correct. What do the particles do? They pass straight through. Okay? There's no reason for them to bounce backwards, okay, or really deflect much. They might encounter an electron, and that might cause them to bend a little bit, but that's about it. So we would expect all of our particles to impact on the direct other side of the gold foil. Okay? And when I initially taught this, I like to say that Rutherford actually didn't like Thomson. Because if he liked Thomson, he might say, well, I'm going to build an experiment to prove Thomson's correct. If we go through and look at this, where did he put his detector? It's all the way around the piece of foil. If Thomson's model is correct and that's all he's trying to prove, where does he need his detector? Just at the other end. He actually put it all the way around. That sounds like a waste of material if Thomson's right, because nothing should bend back. Okay, but it's good that he did wrap it all the way around, because what did he find out? Some stuff came directly backwards. That makes no sense with Thomson's model. Okay? Because Thomson's model says really the electrons are the only thing that have any mass. If anything, our alpha particles will stick to the gold foil. They would never bounce. Okay? That's a pretty phenomenal discovery. What does that discovery then mean? If things are bouncing, what are our alpha particles hitting? More than just the mass of the electrons. Add to it, should they be hitting electrons? No, because they'd be stuck to the electrons. So if they're bouncing, what are they hitting? They're hitting something positive. And not only hitting an individual positive, they're hitting something big enough to cause them to ricochet the other direction. Okay? So those protons, or those positively charged things, must be all located in a singular place. So that when the alpha particle comes through, most of the time, what happens? They go through. And I just see the back side of it light up. But every so often, the alpha particle comes straight in and impacts directly where all the positive charge is located. At that point, we now have enough mass and repulsive force of those charges that what happens? The alpha particle ricochets backwards. It is that ricochet effect that disproves Thomson's model and allows us to come up with Rutherford's model of the atom, which we'll look at here in a second. Right? So that's kind of neat. Right? Before we dig too much further into Rutherford's model, one of the things that hinges on this is that I have alpha particles. Well, what the hell is an alpha particle? Okay, could you go to the store and buy alpha particles? No. Where do alpha particles come from? It's a form of nuclear radiation. Okay. How safe is nuclear radiation? Okay, so we at least acknowledge that nuclear radiation is not safe. One of the things that's happening with nuclear radiation is that the nucleus is so unstable that it falls apart and it emits these radiative forms. At this point in the game, at this time, they don't know it's nuclear, they just know it's radiation. Okay, they are able to determine that they're positive, and they are able to determine that they have mass, but that's about it. They don't know where they're coming from. Okay. We found that some elements release this radiation. And in the process of them releasing that radiation, they change their identity. Okay? That becomes a little bit weird, because if a sample starts as one thing and it starts to become something else, when I now look at that sample, is it pure anymore? No, it's now a mixture of a bunch of different stuff. Okay? Which that other stuff is now doing other forms of radiation. Which means in that sample, not only is it not pure, but now it's doing a bunch of different things. What if one of those things just happens to decide, well, I don't like passing through gold foil, I'm going to bounce? That's now going to give a false result. So when we run this test, I have to make sure that that source is only emitting alpha particles. So I have to find a pure source of that. Okay, well, it is a radiative process. Somebody needs to go out and find an element that naturally releases alpha particles and purify it from the rest of the junk found in solution. Okay? It is exceedingly rare to walk out into the environment, bend over, and pick up, boom, this is now a pure sample of copper. Okay? Really, the only reason that happens now is that we as humans have refined copper and now have copper pipes and such elsewhere. But if we're going to pull that copper out of the earth, it usually comes in the form of an ore with a bunch of other junk in it. Okay? So somebody had to go out, pick up some samples, and be like, well, that's got a bunch of crap in it. I want to get rid of all the other junk and only look at the thing that is radioactive. Okay? That's not an easy process. That process would involve lots of research and time to go through and discover it. Okay? If we scaled that to potentially modern times, okay, is there something that is potentially plaguing mankind now that we might want to solve using science or chemistry? Global warming, fair enough. Try something else. Cancer, thank you. That's the one I wanted. Okay, we got lots of problems, but let's pick cancer. Okay, there's lots of people working on cures to cancer. So let's say you go into the lab, you now discover the cure to cancer. It is this drug. What do you do with that information? Okay. So if anybody happens to watch your lecture and the morning's lecture, unfortunately you guys failed the test. Write a patent. Why are you writing a patent? So no one can steal it. What is the point of you writing the patent? To make money. Okay? With that patent, you can now control that information and you can make money off of that. Okay? There's some big kind of ethical issues there. You just served or solved a major health crisis for the world, and now you're going to control whether people live or die based off of the price that you've established for that. That's a potentially dangerous situation, and there are some kind of ethical dilemmas there. The flip of that ethical dilemma is, what did you just spend your lifetime trying to do? come up with that cure. So you spent time, effort, money to find that cure. If you don't patent it, there then becomes the possibility that you don't get any of payment for all that time that you spent in it. Okay? So finding that balance is a pretty tricky thing to deal with. Okay? The reason why I like talking about the alpha particles is the person that discovered that purification for alpha particles did what with that knowledge? Made it publicly available. Okay? For free. No patent. What does that mean happens? Well, now everybody else has access to that information and can use that information to then potentially study other things, right? Without having to deal with the potential firewall of the patent process. Okay? So that is an exceptionally noble thing to do, while at the same time kind of stupid, because they just spent their lifetime finding this information and now they don't get the payment for it. Add to this, it's radioactive. They've also probably poisoned themselves with this work and don't get any of the financial rewards from it. Okay? So I do put them on kind of a high pedestal there because they decided to go the complete opposite, let's save myself, and kind of went completely selfless to try and advance scientific knowledge. Okay? Who was that person? Mary Curie. Okay? And that's an interesting discovery in and of itself. They've now shared this information. We're talking early 1900s. This is a woman that discovered this information. Oh my God, women can't discover anything. Women can discover lots of things. Okay? They're really good at it. Okay? Why is that something to call attention to in this era? Could women vote? Did women really have any rights at this point? Pretty much none. Okay? So someone that had actually information effectively removed from their periphery was still able to go through and make these discoveries. And not only after all of that kind of roadblocks preventing those discoveries, still said, here you go, rest of the world, have this information, without trying to hold that information back. So I think that's pretty phenomenally cool. Okay? The rest of the world also thought it was cool because what did Mary Curie eventually get for this? A Nobel Prize. Okay. What's that? Yeah. Continue with this. There are two people in the world to have, in lifetime of the Nobel Prize, to have earned the Nobel Prize twice, okay, in different fields. As a fun fact, both those people are chemists. I wasn't one of them. Okay? Mary Curie is one of them. She got a Nobel Prize in chemistry. The other chemist is Linus Pauling, who also got a Nobel Prize in chemistry. Pauling's second Nobel Prize is in peace. Okay? Not that peace isn't a big problem, okay? But if we compare, like, I don't know, peace to science, most people tend to say science is more difficult. Or that may just be my arbitrary science person getting in the way. So Pauling has kind of a humanities Nobel Prize and a science Nobel Prize. What does Curie have? Chemistry and physics. Okay? Two of the arguably most difficult science fields there are. Okay? So it's pretty freaking intense. Okay? So extremely brilliant, kind of selfless, because she's sharing this information. Okay? To get back to the whole, she's a woman in science, and that's ludicrous. We just said Nobel Prize, right? She did most of her work in France. Every country has their own National Academy of Sciences. She has 2 Nobel Prizes. The French collection of scientists look at her work and go, you're a woman. And they exclude her from their society. Right? That's kind of encompassing of how women were treated in science, and kind of still treated today. Okay? Not quite as bad. What's that? Bunch of jerks. Okay? They did, in their defense, later go back and after she died, retroactively added her into the society.
That's like saying you graduated high school. Oh wait, you never been to school. You graduated high school, you go back and you get.
Yeah. Okay. So it is kind of an interesting story. Some of you will be studying her, and you'll be hearing more about her as far as the background goes, because what I've got is kind of hand-wavy at best. Okay? But it is kind of a neat story, in my opinion. Remember the whole, I talked about the whole radiation being dangerous for your health? Have you heard how she died? Radiation poisoning. Why did she die of radiation poisoning? Where did she keep her samples of radioactive materials? In the front shirt pocket. Pockets of your pants? Yeah. Right? That was initially how it was marketed too. Right? So she exposed herself to this radiation for the sake of science and then later died for that same exposure. And it's not like they didn't know it wasn't dangerous either. So we talked about in lab, like how many of you would ever stick a pipette in your mouth to suck liquid into the pipette? You're like, that's stupid, you wouldn't do that. That was basic science protocol. Same thing in Curie's age. Okay? Radioactive stuff. I know this is dangerous, but I'm just going to carry it around anyway. Right? Remember how we started out, scientists? Scientists were egomaniacal. I know this is dangerous, but I'm more important than the science, so I won't get hurt. It's not quite true.
That's why joking helps you out a table of Horcrux of science.
Yeah. So, Curie releases that information, gets us the alpha particles. Rutherford, ultimately Rutherford's student, remember how we talked about that with Millikan, could go through and decide what was going on with our gold foil and came up with a new model for us. Come on, new model. Whoop. There it is, there's our new model. Is that a hand?
Yeah, wait, so is that a single element that's deflecting all the alpha particles?
It is a single atom, and in fact, it's worse than that. It's a single nucleus that's reflecting it. This sheet here is a collection of a bunch of atoms.
But like this thing that's like emitting all the light in the alpha particle, is that a single element off the periodic table that's doing that?
Oh, that's submitting that? It's radium.
Oh, that's what it is.
Yeah. It's a collection of radium atoms. Yeah. That's the source of alpha particles. So our alpha particles come out, and we'll talk about, potentially talk about radium later. Okay? We see this bouncing. That means Thomson's plum pudding model, as exciting as that name was, is wrong. This is where Rutherford says we have a nucleus. Okay? Why do you pick nucleus? Not neutral. Neutron goes back to neutral. What is nuke? A nuclear family. Doesn't mean we're explosive. Okay, central, I believe, is our root on that for nuke. Okay, is that right? You looking it up for me, Greg? Yeah. It comes back to our Latin roots for kind of central. It is central.
Core, central part, heart.
Okay. So what he went through and did was said that we have effectively the heart of the atom, and that heart of the atom is where all the positive charge goes. That's where the protons exist, which immediately brings up a big issue. What happens when I bring an electron near another electron?
They repel.
They repel. What happens when I bring a proton near another proton? They repel. Where did I just put all the protons? In the middle, right next to each other. Which would then mean they should all repel. Okay? There's no reason they should all stay there. Okay? So based off of this evidence, Rutherford then further theorizes the existence of something else. There has to be something else present to keep the protons all there. There has to be a glue. What properties of this glue might I expect there to be? Should they be negative? No, because then we'd have electrons. Should they be positive? No, because then we have more protons. Okay? So what are they? Neutral. They should have no charge because otherwise they would interfere with the other particles that we know to exist from Thomson's model. Okay? So I need to come up with a fancy name for a neutral species. And I end up with neutron, electron, proton, neutron. Okay? Amazingly, they have kind of an organization behind that logic. Okay? There was a question about though it was all to do with that, and I was instead referencing the gold foil here, to get an idea of scale of the nucleus. Okay? If we go through and take an atom, we can look at an atom has a diameter 10 to the minus 8 centimeters versus 10 to the minus 13. Well, that's only a difference of 5. That can't be that big a deal. Like if I'm 6 feet, 5 feet is a foot, you could still see that, right? That's not that big of a difference. Our brain does not do well with powers of 10. Add to that, we don't do well with negative signs. For all of you who think you can do well with those, you will either be an awesome physicist mathematician, or you will realize shortly through your science career that you aren't very good with dealing with negatives. Okay? Most people fail with negatives. Okay? It is hard to keep track of them. Okay? So let's put that into terms that make a little bit more sense. Let's make the atom the superdome, right? Big football stadium. The nucleus would be a marble inside the superdome. Right? You can imagine how tiny a marble is just in comparison to us or this room. The superdome holds the football field and all the peoples. Like, that's a pretty massive difference. Right? So if we go back to the experiment, we are seeing a very rare occurrence for it to bounce back because the nucleus is that tiny. Doesn't happen often, it just has to happen. And because we got lucky enough to see that, we know that's what's going on. Okay. Kind of cool. So Rutherford says we have a neutron. We have that neutron because I can't put all the positive charge in the nucleus. Okay? Those charges should repel away from each other. He did not experimentally prove it. He just said it makes sense for it to exist. Okay? We need to have it. It wasn't until some later date, 1920s or 30s, I think, that James Chadwick came through and actually experimentally discovered the neutron. So he built an experiment to say, this is what's up. You guys got a question? No? Okay. All right. Just because I think it's neat, Rutherford was Thomson's student. So Thomson went through and did these experiments, or helped to design these experiments. In the process of Thomson studying electric charge and electrons and all of that, Rutherford was in his lab working with him as a student. Rutherford then graduated, went on and created his own studying process and came up with the model of the atom. Guess who was Rutherford's student? Chadwick. Chadwick then studied under Rutherford, left Rutherford to come up with the next theory on neutrons, or the experimental evidence for neutrons. So it's kind of neat, somewhat incestuous, if you will, because it's kind of coming from the same group. Okay? So the big summary that comes out of all of this is in the red table at the bottom. You need to know the name of your particles, the symbols we associate with them, where they're located, their relative charges, and their relative masses. I always find this a bit odd that they decided to drop this in for the relative mass here. Okay? 1 over 1,836. Okay? Anybody want to memorize that? Okay, no. So let's come up with a reason for why we don't have to memorize that. Okay? Does hair have mass? Yes, so it contributes to my mass. So if I step on a balance to get my weight, okay, I would have a reading. I want to lose weight, so I rip out a hair. Does my mass change? Does the scale change? No. Why does the reading on the scale not change? The mass of my hair in comparison to the mass of my body is so insignificant that the mass of the hair is effectively 0. What is the mass of an electron when compared to the mass of protons and neutrons? 0. So you should be memorizing the mass of an electron is 0. Okay? Kind of, sort of? Okay. So, chapter 4, we've got these scientists listed out. Okay. You have, so that's what, 5? 5. There are 3 more scientists in your lists of people that you could potentially study. We'll talk about at least 1 more, maybe 2 more, and I'm trying to remember who that 3rd one is that we haven't talked about. So who are the 3 that are missing? Mendeleev, Ramsey, those are the 2 I remembered. Chadwick, we already talked about Chadwick. I don't know why he's not up there. He should be up there.
Is it Thompson or Thompson?
It's actually Thompson. I'm pretty sure I screwed that one up. I don't think there's a P. So in your research, because Thompson and Thomson can easily get confused, make sure you're looking at the right one. Okay. In your research, make sure you're looking at the one that discovered an electron. Okay. Which was actually not 19, I think it was like 1898, right around there. Okay. Before we continue into chapter 5, we want to move into this concept the textbook presents as atomic notation. Okay. I would make an argument that this has nothing to do with atomic notation, okay, at least as they're presenting it. Okay, so our symbology is down at the bottom, and then we've got some examples of what's going on above. So we have our symbol, okay, SY, which happens to be what element? As you're all really struggling to look for it, right? SY for symbol, okay? It's not an actual element, okay? It's just the 2-letter abbreviation for symbol. Okay. Lower left-hand corner is what we would specify as Z, because we're going from A to Z. That's my only guess for it. Okay. And Z represents the atomic number. The atomic number is the number of protons for that element. Okay. A is then the mass number. The mass number is the number of protons and neutrons. Okay. Where do you find the protons? Z is a fair answer, but not the answer I'm looking for. Try again. On the inside, I'll also accept that. More specific, nucleus. Where do we find the protons and neutrons? Nucleus. Where in this notation have you seen anything about electrons? It's not there. When we talk about an atom, what particles are there? Protons, neutrons, electrons. This notation mentions nothing about electrons. Okay. So is it referencing the atom? No. What is it referencing? The nucleus. I think there's a very solid argument that what we're actually looking at here is not atomic notation, but the nuclear notation. Okay. Which is going to bring up one of the kind of apparent discrepancies here. Okay, so let's pick an element to work with. What element do you want to look at?
Boron.
Boron. I always like boron because it sounds like moron. Like boron. I feel like calling people like boron. You're a boron. But I don't think very many people would get it. Okay. What's that? No, it wasn't a joke. That's just what I want to call people. Well, boron. But it's not really insulting. Okay. Maybe I should have kept that as an internal monologue. What would the atomic number be for boron? Step back. Boron. B-O-R-O-N. What is the symbol for boron? B. How do you know it's B?
Because it's in the boron group, the very top one.
So when I look at the very top, I see H, and that's no.
If you go over to the right, and then it's before the C.
But BE is before C too. Why is BE not boron? Okay, N comes after C. Why is N now not boron?
Because B is boron.
B is why is B boron?
It's the first letter.
You guys are all struggling with this, and it's a really simple answer. Someone said B was boron. That was it. It's been defined. How do you know what those definitions are? Are you responsible for knowing that? Yes. Okay. Remember we showed the periodic table and I had that thing on it that said elements for memory? Okay. And you need to look for that elements for memory file, which I believe is in Canvas. And it lists something like 70 elements, just their names. You need to know their symbols. Okay. The ones that are bolded, you absolutely need to know the name and symbol for. Boron happens to be one of those. That's how you know it. It is a definition. Okay. How do you know my name is Mike? Because I told you. It's a definition. You're responsible for that information, just like you're responsible here. Okay. So, next part. Do I want to look at the mass number or the atomic number? Take your pick. Okay, atomic number. Good pick. Where's the atomic number found for boron?
The 5.
Okay, it's 5. How do you know it's 5?
Because the it says.
It says doesn't quite work. I know where you're going. Okay, so I should write 5 underneath the boron. So when I look at the periodic table, 5 is written underneath the symbol for boron.
It's the smaller number.
It's the smaller number. Unfortunately, that observation will always be true. So I can't counter it for that reason, but it's also not correct. How do I know 5 is the atomic number? It's, again, one of those kind of simple answers. There's this little device on our periodic table that tells us what the numbers mean, like when they show up in different places. And when we look at the upper right-hand corner, what do we say it says? The atomic numbers. When I'm asking for the atomic number of boron, all I got to do is look in the upper right-hand corner and 5. That's how I know that's the atomic number, which you probably did. I'm not going to lie. I bet you did that. You just didn't tell me that. Remember when we asked for what is your process for how you find information? Telling me because it is doesn't work. Telling me because the legend on the periodic table tells me that information, that does. Does that make sense? Okay, so we got the 5. Last piece of information, mass number. 10.81. What is the mass number? Protons plus neutrons. Can I have a fractional proton? Rhymes with show. No. Can I have a fractional neutron? Rhymes with snow. No. Whole numbers. I can only have whole number of protons and neutrons. Snow was a bad example. Show was better, in my opinion. Okay. If you're telling me the number I should write there is 10.81, what's the problem?
It's not a whole number.
That's not a whole number. Is the mass number specified on the periodic table? No, it is not. What is specified on the periodic table? The atomic weight, which admittedly they shouldn't be calling it weight. They should be calling it atomic mass. Either way, is atomic mass or atomic weight the same thing as mass number? Unfortunately, not. Okay, and we will discuss what that not is, or why it's not. The mass number, by definition, is the number of protons and neutrons. It is not found on the periodic table. Okay? So to figure out what that number is, I have to give you a little bit more information. I'm going to say we're looking at boron 11. What does that 11 represent? Nope. If it was the atomic number, it would be the mass number. And we would specify that number in the upper left-hand corner. Okay. The mass number and the atomic weight or atomic mass are related to each other, but they're not the same. Why, on our periodic table, would it place the atomic number at the top and the mass number, or sorry, yeah, the atomic number at the top and the mass-ish at the bottom, whereas in our nuclear notation, they put the mass number on top and the atomic number on the bottom. Easier to organize. What do you mean easier to organize?
Like you can put the elements like number.
Okay, if we look at the periodic table, what comes after 1? 2. 4 also comes after 1, but it doesn't come after directly in sequence. So if we organize by atomic number, we can see a direct sequence moving through the periodic table. Okay, by putting that up at the top. Why would we put it at the top? Open up a book, read the first word. Where's that word located? The top, left. I get left and right's confused too. But it's at the top, regardless of whether it's left or right. Okay? So why would we place that number on the top on our periodic table? Because we're trying to draw attention to that organization first and foremost. After that, we can draw in the symbol. After that, we can draw in the mass. Why then, nuclear notation, switch it to put the mass number on top?
So you can subtract the 5 and get the number of neutrons in the nucleus?
I, for whatever reason, have never heard that answer. And that's a nice, easy way to look at this. What he's suggesting is to find the number of neutrons. What do you have to do? Mass number by atomic number, and we now get 6 neutrons. It fits the mathematical expression. If we'd altered it the other way, 5 minus 11, and I would have gotten -6, and that doesn't make sense. So cool, mathematically, that's a neat little expression. So if you're in the nuclear notation, that would help. Okay. My argument is it's not for that reason. It could be.
It worked.
It definitely worked.
That's awesome.
Okay. When would I be concerned about the nucleus?
With isotopes?
Sort of. Is anybody concerned about the element carbon? And you're like, well, why would I necessarily be concerned about it? Okay, so let's switch it up, because you're probably like, I'm not concerned about any element. Uranium. Are you now concerned about uranium? What changed?
The number of protons?
Okay. Uranium, what do you have associated with uranium? It's radioactive. Why is uranium radioactive? Because it is. It's unstable. What is unstable about uranium? It gives off radiation. What type of radiation does it give off? Nuclear radiation. Who cares about the nuclear notation? Nuclear physicists. And they're concerned about nuclear decay. When is my nucleus going to fall apart? When the proton and neutrons aren't balanced out right. What determines the number of protons and neutrons? The mass number. So as a nuclear physicist, what's the first thing I want to see? The mass number. So I'm going to put the most important number to my field in the place where I would expect to find it as I read left to right, top to bottom. Where is it written? The upper left corner. I think that's why we use this notation. Because a nuclear physicist needs to see that number. And when he sees that number of 11, or she sees that number of 11, don't care. So when would we expect to see radiation? So uranium, you all freaked out at. What if I said plutonium? Okay, some people are saying, yeah. Where are uranium and plutonium? There's uranium. There's plutonium. Okay, I could throw out a couple others that you would probably be like, I have no idea what you're talking about, and I don't really care about that one. Okay. Uranium and plutonium happen to be some of the most famous. Okay? I could throw out one more that you should arguably be like, yeah, that one's dangerous too. Radium. Okay? What do radium, uranium, and plutonium all have in common? How would you know they have a higher amount of neutrons and protons? The atomic weight, but the atomic weight isn't the mass number. What particles contribute to the mass? The protons and neutrons. So it is related to the mass number. If my mass number gets big enough, then I have radiation. Turns out, where is big enough? Right about 200. Okay? Lead is pretty much the last space. After that, pretty much everything afterwards is radioactive. Okay? I can get radiation further up in the periodic table, but for the most part, it's everything after lead starts as radioactive. Okay? Well, why does it get so big? Why does then the nucleus start to fall apart? What have you done to get to uranium? How many protons are there?
92.
92 protons. What do those protons do when they see another proton? Repel away. So what do you have to add to make sure that those protons stay there?
More neutrons.
Neutrons, effectively a glue to keep it there. At 92, how much glue have I added? A lot of glue. If I'm just going to start gluing together marbles, right? Okay, I put a little glue to put two together. That's not that bad. To add a third one, I need more glue. To add a fourth one, more glue. And as I continue to add marbles, I progressively need more and more and more and more glue. Eventually what happens, okay, particularly if I don't give it time to dry and set in between each of these additions, it falls apart. And it falls apart as a big mess. It turns out nuclei are doing the same thing, except they fall apart in predictable patterns. Okay? So we don't get the exact parallels, but they're pretty close. Okay? Is that a question you got there?
When you're done, or when you're about to go to the next slide.
You should ask, I think.
Well, it's more like, okay, so.
Go for it.
So I've been trying to find a good point to bring this up, but Mike's been going through different types of notation, right? Notation is a key word to look for when someone's going to talk about atomic notation, nuclear notation, scientific notation, mathematical notation. That's a signal that they're about to tell you how to translate a particular writing system. We're going to talk more about writing systems here in a few weeks, but Mike, in this way, is actually acting as a linguist and a writer in this way. He's breaking down a specific type or form of communication with certain socially agreed upon norms and conventions. What comes first, second, and third? Does this sound familiar at all? Like we just covered this, right? So I just wanted to point that out as we were going through it. I didn't know if this was a good time to do that.
And
so.
even within the field, we're changing how we organize that information. Most chemists deal with the periodic table, where we have the atomic number on top. But if I move to now a nuclear field, the mass number shifts to being on top. Because the information that I need needs to be drawn attention to quicker. Okay, so depending on where I'm going, I'm going to have different ways to present the exact same information. Okay, which I think is kind of neat.
That sound familiar?
Okay. So ignore that. Sorry, I thought I moved it. So using atomic notation. Okay, so we can go through an example here. I've got the example shown there, and I've got the previous slide kind of answer key shown at the top. So what is the element?
Silicon.
How do you know it's silicon?
SI.
Si. How do you know silicon is tied to Si?
Because someone said it was.
Because someone said it was, and not just that someone said it was, you remembered that someone said it was. Okay? You have to tie all that information in. Okay? The atomic number is 14. How do I know that? That symbol says the atomic number is 14. And I know that the atomic number is supposed to be coded on the bottom of my symbol. I've got my 14. What is that 14 represent? And don't tell me atomic number. The number of protons. So I now know some information about the number of protons. Did I have to have the atomic number to know the number of protons? How many protons does boron have? 5. Did I tell you the atomic number for boron? No. How'd you know the number of protons?
Because it's the atomic number.
As soon as you know the symbol, you can use the periodic table to pull the number of protons off of it, because it is the atomic number specified on the periodic table. So as soon as we write SI, I know there are 14 protons based off of the periodic table. Okay? So I don't have to have that in my nuclear notation. The symbol and the number are redundant in this notation as long as I have the periodic table. Okay? As a chemist, what is something you should always have with you? Periodic table. That's effectively your dictionary. Okay? We want to always keep that on hand so that we know those references and we can find those numbers. Okay? With a mass number of 29, what do I know? Not quite there yet, but yes? It's the number of protons plus the number of neutrons. With the added information from the previous one, the number of protons being 14, I can now do that difference to tell me that the number of neutrons is 15. Yeah. Make sense? You all good with that? Okay. Atomic structure in the periodic table, because we already did those first 4 columns, in today's lecture, we're not going to treat it as a review. I don't want you to tell me what those first 4 columns are. What I want you to do is tell me what that last column is. What does it mean? Right? What is the meaning of the number of electrons? What is the meaning of the number of protons? What is the meaning of the number of neutrons? Right? And if you can't come up with a guess for any of those, start filling in the rest of the table then. And I'll give you 30 seconds to kind of think about it, and then I'll give you another couple minutes to talk to people around you, see if you can come up with a meaning. That's a fair question. Did anybody have any ideas on the meaning? It's a hard question. Right? If you don't like the question, rephrase it. Right? Some people don't like dealing with kind of vagaries? And vagary, I think, is wrong.
Vegas.
Ambiguities. People don't like dealing with ambiguous questions. Okay? So quantify it. Right? Pick a number. Okay? A suggestion was made 50. It's a really big number, but we can deal with that. What does it mean if you have 50 electrons and an atom? Does it mean that? Right? I don't necessarily know that, because each of those pieces are independent of each other. Right? So I think that means I have 50 electrons and an atom. I don't have any more information I can add to that. But what if I have 50 neutrons and an atom?
Doesn't mean anything either.
Well, that doesn't mean anything other either.
At least
Okay.
an atomic mass of 50 somewhere.
Okay, it has at least an atomic mass of 50. So there we could start whittling away at some information. I know that that element must be vanadium or higher if I have 50 neutrons. Right? Because titanium has a mass less than 50. Okay, so cool, that was actually some information. Instead of it being a possible 118 different answers, we're now down to 118 minus 22. So we're about 100 different answers. Okay, odds are that's better odds. Okay, if that's Vegas, you might as well. Like, you've got some better odds there. Okay, but those odds still kind of suck. Okay, the way I would look at it, if you got 1 out of 118 right on an exam, or even 100 right on an exam, I'm not going to be happy as an instructor. In theory, you won't be happy as a student. Right? What if we had 50 protons in an atom?
Then it would be.
Wait, what?
Can't change the amount of protons without changing the element.
If I change the number of protons, I change the identity of the element, which means what is the meaning of the number of protons?
The identity of the element.
It defines or identifies our element. Okay. Once one piece has been solved, now I can start to layer in the other information. So now I have 50 electrons on a tin atom. What can you tell me?
It would be positively charged.
50 electrons on a tin atom. How many protons does a tin atom have? 50. So if I have 50 electrons and 50 protons, what can you tell me? What would its charge be?
Neutral.
It'd be neutral. What would its charge be?
0.
0. You now have 48 electrons on a tin atom.
Then it's positive.
It's positive 2. Right? 48 electrons, 50 protons. Each electron cancels out a proton until I'm left with 2 protons. What's the overall charge on the atom? Plus 2. What if I had 51 electrons on a tin atom? It'd be -1. So what does the number of electrons tell me?
Charge.
It defines the charge. And for those of you saying, don't the protons contribute? Yes, but the protons define the element. Once my element is defined, I can't change the protons, because then I change the identity of the element. So what do the neutrons define?
The mass.
Now the mass. Because once I know I have 50, well, actually it's not that far off, 50 neutrons on a tin atom, I now know that the mass of that atom is what? 50 neutrons on a tin atom. It's 100, because I know tin has 50 protons. So I can add those up. I now get the mass. This way, when I see questions about the identity of an element, I now know I need to look at the protons. If I see a question about the charge on an element, I have to look towards the electrons. Okay? If I need to know the mass, I have to look for the neutrons. Okay? Yes, they're all centered and tied around protons, okay? But it's that extra piece of information that I need to know. Kind of make sense? Okay. What if I had 51 neutrons on a tin atom?
Mass would be 101.
It becomes 101. Okay? It doesn't change the identity of the element, but its mass changes, which means I could have 2 elements that are the same element, but they have different properties. Okay? Mass is a property. So I would be able to just tell the difference between them based off of their mass. What does that mean about Dalton's second law?
It's false.
Dalton's second law said all elements or all atoms of an element are all completely identical, which is not true, because I can change the number of neutrons and it can change the mass. Okay? And the charge. We're going to ignore the quiz for the moment. We'll see that at a later date. This can come in for our isotopes. Okay? Our neutrons defined the isotope. Well, really what an isotope is just a different mass for that same element. So if we take a look at the element hydrogen, it turns out that it has multiple isotopes, the 2 most common of which are hydrogen with how many neutrons? I'm being a jerk, by the way.
0.
0. Why is it being a jerk by pointing at the 1?
Because that's the number of protons.
That's the number of protons. It has 0 neutrons, because otherwise the mass would become...
2.
The second isotope of hydrogen has 1 neutron. Right? Let's take a look at the first isotope. In its nucleus, what is there? 1 proton. What else is there? Nothing else. It's just a proton. What would be the name of the hydrogen atom with only 1 proton? What would be a good name for its nucleus? Well, what's in its nucleus? I can't call it a proton, sort of. So I'm going to call it protium. What happens if I look at the nucleus for the other isotope? What is in its nucleus? One proton, one neutron. So I could call it protoneutronium, because it names each of the pieces, right? The prot and the neut, like there, just like me. Instead, we call it deuterium. What? Why do we call it deuterium? Ooh, that's a good one. Not quite perfect for what I was going to do here. Deuce. Okay. Duo also goes along that. If we look at the root of that name, what is the root of deuterium? 2, referring to the number of particles in the nucleus of hydrogen. Turns out that there is another isotope for hydrogen, which we'll look at real quickly here, but then ignore. 3,1 hydrogen. How many neutrons are in this one? 2. How many particles are in the nucleus? 3. What am I going to call this one? Tri, because that's our Greek prefix.
That would be the root. So we tag in on the suffix. Tri would be the root.
Okay. I don't know, I believe that. But I'll accept that.
Actually, well, okay, so with this one I would say there's not, you have.
There's not, yeah, we don't really
There's not
have.
a clear root, so
Yeah.
it's prefix.
It's prefix suffix. The root is T. No. And we end up with tritium. Where's that name coming from? Tri, because there's 3 particles in the nucleus. Okay? So we could theoretically go through and name every single isotope on our periodic table. Do we want to do that? No, why not? The chemical properties of deuterium and protium are so similar that we can group them as just the single element hydrogen. They don't count as a new element because the chemistry is too close to distinguish it from being something else. Okay? So, what do we do with these isotopes? I now want to think about, say, the atomic weight of hydrogen. Okay, well, the atomic weight has to do something with the mass of the particles going into it. Which particles contribute to mass? Protons and neutrons. Okay? Well, I have 2 different forms of hydrogen. What is the mass of the first one? 1. What is the mass of the second one? 2. So if I go through and say the mass for hydrogen is 1, am I correct? No, because deuterium is also hydrogen and its mass is not 1. Okay, well then I'm going to say the mass of hydrogen is 2. Why am I now wrong? Because protium is 1. How can I come up with a mass that takes into consideration the mass of both? Yeah, I can take an average. What would be the average mass of these 2 particles? How do we calculate that?
Add them together and divide it by 2.
We add the masses of our 2 particles, 1 and 2, and I divide by 2. Right? Really simple. And what do I get for a mass? 1.5. So the atomic mass for hydrogen is 1.5. Jeremy, where did you just look? You looked at the periodic table. What were you looking at on the periodic table? You were looking at the atomic mass for hydrogen. Why? Because I just told you the atomic mass for hydrogen was 1.5. And what did you immediately decide to do? Doubt me. That's harsh. So now the rest of you are looking at the periodic table for the atomic mass of hydrogen. And what do you find? It is not 1.5. Good job. Okay. What did we assume in this calculation?
That there's an even number of protium and deuterium.
That there's an even number of protium and deuterium, that they make up an equal percentage. Well, do anybody see a percentage in that calculation? No. So how is it factored in there?
By using a weighted effort.
I'm saying it's already in there. So the question is how did it get in there? Because you didn't explicitly say factor in the weighted percentages. Our assumption is that half of the sample is protium, half of the sample is deuterium. What would the percent of protium then be? 50%. Okay, numerically, what would that be? 1/2. Okay, or 0.5 if we wanted to. I'm going to get rid of the 0.5. I just want the 1/2. Right? That's how I could calculate 50%, 1 out of 2. Okay? My argument is that we've already factored that into this calculation. Really? Yes, sir, we have. Let's play some mathematical games. This is 1 over 2 plus 2 over 2. Everybody agree? Yeah, we're allowed to separate that out. This is 1 over 2 times 1 plus 1 over 2 times 2. What is 1 over 2 representing in our calculation? The 50% assumption is already factored into our equation, but based on how we set up our average, it becomes implied and we kind of ignored it. What we're doing in that calculation is already a weighted average. We have the percent composition of A times the mass of A plus the percent composition of B times the mass of B. When I do that calculation, I end up with the atomic mass. Right? In math, we would look at this top one and call it a simple average because we didn't intentionally look at the percentages. Right? If we intentionally look at the percentages, it now becomes what is known as a weighted average, because I'm now associating greater value to different masses. Right? It's ultimately the same thing. It's just a question of how much do you recognize those internal assumptions and those internal calculations. So every time we go through and run a calculation, this is what we're doing when we determine the atomic mass. Right? So let's factor in some kind of numbers with this. Okay. So clearly the percentage of each is not 50%. That was a false statement. And we know that was false because when we calculated that average, did it match the periodic table? No. So which one do you think has the larger percentage, protium or deuterium?
Protium.
Why protium? I'll kind of accept that. What's our weighted average? 1.01. Meaning that number is closer to what? Protium or deuterium? Protium, which means larger percentage of protium. How much? You guys ready to test me on this? 99% of hydrogen is protium. 1% is deuterium. So if we set this up, we get 0.99. Why 0.99 and not 99? What does that percent mean? Close, more literal. Per-cent being century, 100. So when I bring that percentage into a calculation, this is actually 99 out of 100 times its mass, which is 1 plus 1 out of 100 times 2. You enter that in your calculator, guess what you get? 1.01 and some other numbers that I don't remember. Magic. Yes? How would you find out what those percentages are? Experiment. How many of you can do an experiment in this lab to figure out those percentages? You can do an experiment to figure out those percentages? You should talk to me after class because I'd like to know that. Okay. I'm going to make the argument you can't. How would you figure out those percentages? Can't do it by experiment.
Google it.
Can't use Google
So-
on a test.
Why can't you just multiply the protons by 2, see the difference, and then figure out?
So careful, multiply by 2. Why do you want to multiply by 2? I'm going to make the argument because here we're saying there were 2, so you're saying I should multiply by 2 to deal with 2 different isotopes. Nobody said that there are always 2 different isotopes. And in fact, like 5 minutes ago, what did I say? There's 3 isotopes for hydrogen. Tritium just happens to make up such a tiny, tiny percentage that I can get away with 99 and 1. It's more like 98.999, 1, and 0.0001 for tritium. Okay? So I can't just say, well, I multiply by 2. The other part, these are different just by 1 unit. When we look at chlorine, there are 2 common isotopes for chlorine. One is chlorine 35. Guess what the other one is? Chlorine 37. There is no chlorine 36. So we can't make the assumption that the neutrons are different isotopes are only based off of 1 neutron. So how would we know? Jump, 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 jump. How do you know? So all that stuff at the top is just about weighted averages. Ignore that because we just talked about it all. Here's a question. How do you know what those percentages are?
Well, I have a kind of a formula that was taught in my pharmacy class actually that I can use to figure out the percentages of the protium and deuterium.
You can show me after class, but I'm going to tell you already, it's making some assumptions that you're not allowed to make. How do you know the percentages of the isotopes for gallium? There's some words on the screen. You should probably try reading those. Don't give me this plug-in stuff yet, because we didn't talk about plug-in anything. How do you know the percentages for your isotopes? They're told to you. You are not expected to memorize those. They're literally given to you. Okay? And depending on what information we want you to solve within that long expression, we may give you both, we may give you one, we may give you neither. We won't do that. Okay? So what you have to do is recognize the value of interchanging those individual pieces. One of the things that becomes challenging, so I'll leave you guys to work on this over the weekend, is that if you take a look at your numbers, gallium-69 has a mass of 68.926. Is 69 the same thing as 68.926? No. Are those numbers really close? Yeah. Is it going to be easy to lose track of those numbers? Yeah. Be very careful with your note-taking to make sure you don't lose track of the numbers and you can keep it organized. Come up with an organizational system that makes sure you don't screw that up. We'll talk about that Tuesday. For those of you that had ideas on how to solve for that,